Welcome back to AP Calculus BC. We're in the midst of our series convergence tests, and we're actually almost at the spot where we can talk about what a series is, but we have a few more things to do. So here we go. In calculus, you're going to find it becomes really useful to evaluate the sum of a certain number of terms, sometimes even all of them, of a sequence. So, for example, if you're given this sequence where you have all your individual terms here, then the sum of n terms of a sequence is given by this notation s sub n, where of course you would replace n with whatever number you wanted, and that would tell you how many terms you're adding up. So, for example, s sub n is known as the partial sum of n terms of a sequence. We're going to go ahead and find a couple partial sums for the infinite sequence given below. S sub 1 means take the first term, 1/2, and then just sum up one of them. Well, it's just 1/2. That is my first partial sum. My second partial sum, though, is found by doing 1/2 plus up to the second term 1/4. And so if we gave this common denominators, of course, we have 2/4 plus 1/4, which equals 3/4. And let's go ahead and look at s sub 4, or the fourth partial sum. 1/2 plus 1/4 plus 1/8 plus 1/16. I think we need common denominators. It looks to me like they all go into 16, so multiply by 8, we get 8/16, multiply by 4, 4/16, multiply by 2, 2/16, plus 1/16, and then sum these up. 10 and 5 makes 15/16. As an alternate to writing the s sub n notation, imagine you wanted to tell someone to add up the first 18 terms of a given explicit formula. Well, instead of writing out all 18 terms, we have a shorthand, and the shorthand is called summation notation. And summation notation is going to feature our uppercase Greek letter sigma. Now, this shouldn't be a shock to you. We've seen sigma before, especially when we defined what integrals were. We used a limit as n went to infinity of sigma, so we've seen this. However, this is just a nice review for you. So, we can define this nth partial sum as the summation of the general term from 1 up to your partial sum, which is, of course, a sub 1 plus a sub 2 all the way up to a sub n. Reminders of some vocabulary. K is known as the index of summation, right? When you write k equals 1 down here, it's known as the lower limit of summation. And of course, n up here is the upper limit of summation. Without a calculator, let's go ahead and expand and evaluate each sum. And then you can actually use a calculator to check your answer. I'm not going to go through this because we did learn this last year, but your calculators all have a sigma button that you can plug things in and check it out. So I'm just going to zoom in and work these through. I would suggest that you pause this video and try it on your own and then come back together after. So go for it. And you're back. It should look something like this, where we have, and we'll try to be pretty quick here, 1 plus 1 is going to give me 2. Okay, and then we substitute in 2. 2 squared is 4. 4 plus 1 gives me 5. Then we substitute in 3, right? This is I equals 1, I equals 2, I equals 3. 9 plus 1 is going to give me 10. And then we do our next one. That was 3, so now we have to substitute in 4. It's 16 plus 1 is 17. We have to substitute in 5. That's going to be 26. So this is just 1 bigger than every perfect square, isn't it? So the next one's going to be 1 bigger than 36, which I think will get us 37. And then we'd have to sum all of these up. You can do it however you would like. I'm not sure if there's an easy way or a difficult way here. Nothing going to be too easy. We could take this 2 and add to, let's say, the 26. That's going to be 28. And then 28 and 17, I should cross these off so I don't lose track. 28 and 17, I think is going to give us 45, and 5 is 50. And then another, let's see, 50 and 37 is going to give us 87, plus another 10 gives me 97. Right? Easy summation stuff. Let's take a look at our next one. Crazy formula says start with a k of 4. Well, if I substitute in 4, I get 1 over 1 minus 1/2, and then I have to add it on to my next term. That's when k is 5. 1/2 minus 1/3, and then we add it on to when k is 6, and that's going to be 1/3 minus 1/4, and then we add this on to when k is 7. That's 1/4 minus 1/5. Now this may look daunting because of all the fractions, but take a look at what cancels. Negative 1/2 will undo the positive 1/2. Thirds are gone, the fourths are gone. This just becomes 1 whole minus 1/5. I think this is just going to be 4/5. Nice. Last one. The summation of the constant 3. Well, when k equals 1, we'd try to plug 1 in, but there's nothing to plug in, so we just get 3. When k equals 2, 3 is constant. K equals 3, k equals 4, k equals 5. There are 5 3's, so I think we end up getting a sum of 15. Now, there are some properties of summations that you will need to be familiar with as we move through the next couple months. In each of the examples below, C is going to represent a constant, and then A sub I and B sub I are going to represent the general term for each of 2 different sequences. The first thing we need to be comfortable with is that if you have a value that is multiplying or dividing, same as multiplication, by a general term, it is completely okay to factor out that general term of your, or factor out the constant from your general term. So in words, what does that mean? Well, I'll let you summarize that, right? If you have a constant multiplying, you can factor the constant outside the summation. Well, maybe an easy example here, right, is if we wanted the sum from, let's say, n equals 1 to 3 of, I don't know, 10x squared, well, then instead we could just find 10 times the sum from n equals 1 to 3 of x squared, which means we just do all the addition in here, and then at the very, very end, we multiply by 10. And that'll save you a little bit of work so that you don't have to multiply by 10 every time. Our second one says that if you have 2 general terms adding together and you are summing them up, then it is okay to split this into 2 separate summations. We'll say I equals 1. I guess I'm using I and k interchangeably. So we have A sub I plus the summation from I equals 1 to n of b sub I. I really should do plus minus because it's okay with either of those. So what does that mean then? Well, what if you had something like the sum of, I don't know, I equals 1 to 5 of x squared plus 3x. It is totally okay to split this into 2 separate summations where we sum x squared and then we sum 3x completely separately. I should be using I here. I'm not sure why I switched to x, and I realize now that I did that up above as well. So I'm going to go back and fix it while you guys are writing. And I used n here, so let's just continue with n and make everything match, at least in variable, if not color. The last one. The last one says that if you have 2 sequences multiplying together, then you are not, and I will say not always, able to split this as 2 separate summations. Now, sometimes you can, and there's no adverse reactions, but I would play by the rules that say basically you cannot do that. So, for example, if you were summing something from 1 to 5, again, I guess I like 5 today, and you had 1/2 to the n times sine of n, it would not be okay to sum up from 1 to 5 of 1/2 to the n times the summation from 1 to 5 of sine of n. Now, again, sometimes you can do that. However, I would operate under the assumption that you cannot. The last part for today is how to actually write a sum using summation notation. And this does a pretty good job of tying together our first couple days of this unit, where first we looked at sequences, then we practiced general terms, writing those formulas of sequences. It's a little bit weirder with our summations here. So I will say generally what people do is you write a formula for the general term first. Okay, And then you pick what value is going to be at the bottom of your limit, that limit of integration, right? Not integration, that limit of summation here. It's generally accepted that you start with 1. However, it's okay to start with 0 or some other positive number, and your book is going to throw a bunch of different options at you. So let's look at a quick example. Imagine you were summing up 1 cubed plus 2 cubed plus 3 cubed all the way up to 7 cubed. Well, the first thing you'd want to do is write the general term. And I think you can tell the thing that is constant every time is that there is a cube. So there needs to be a cube in your answer. The thing that is varying, the variable here, is that 1, 2, 3, the base. And so that's where the a comes from, or I cubed or k cubed or whatever sounds good to you. The next part is you need to write this in summation notation. However, again, that lower limit of summation really makes things interesting because you can pick any value you'd like. For example, I bet most of us would have said, well, let's just do from 1 to 7 of I cubed, because then when you substitute in 1 here, that's where the 1 cubed comes from. When you substitute in 2, 2 cubed, all the way up to 7 cubed, and that's fine. However, you might have also realized that you could have started at 2. If you start at 2, you have to play around with the formula a little bit, but if you substitute in 2 here, 2 minus 1 is 1, and then there's a 1 cubed again. However, since you bumped n up by 1, then you would also need to bump your upper limit up by 1 as well, and now we're going from 2 up to 8. Easy way to check, if you substitute in 8, 8 minus 1 is 7, and so we end with 7 cubed. Or, of course, you could have started with an n of 0, if that sounds more fun to you. You will notice these all should have been i's. I'm not quite sure why I switched back and forth with I and n. Your book likes I like n, so I don't know, we're trying to make both worlds meet. Yeah, you could have also done I plus 1 cubed for I equals 0, and if you substitute in 0 here, 0 plus 1 is 1, and you get 1 cubed, right? Nothing too terrible. Here we go. Oh yeah, last but not least, regardless of whatever your lower limit of summation is, if we're using this partial sum notation, S sub 5 doesn't mean add up the first 5 terms. Rather, what it's telling you is to sum up all the terms from the lower limit and stop when you get to an input of 5. So let's take a look here. If you had this summation, right, then S sub 5 here would mean start at the lower limit and plug things in until you replace n with 5. And so that gives you 1, 2, 3, 4, 5, 6 terms. So S sub 5 doesn't mean add up 5 numbers. It means add up all the terms until you plugged in 5. Or if you had this summation over here, S sub 5 would mean start at 1 and then go to 5. And notice here you only have 5 terms. Or if you continued even further, you started at 3 to 5 and you wanted the partial sums up to the 5th value, well, since you're starting at the 3rd, there are going to be just 3 terms here. You'll need that again for the next couple days, and we'll keep reminding you, so no worries. Okay, now you get some practice. The practice is 10 problems, right? Looks like 10 right here. Very nice. And you have 2 things to do. First, you're going to have to identify the general term, and that should be review. We did general term stuff a while ago, a sub n equals something. And then the second thing you'll need to do is convert that general term to summation notation. So try each of these, see what you can do. If you need a hint, you can watch me work through the first one. Once you finish, you can watch my video to make sure you got everything right. And I think that'll take you to the end of today. So here we go. Hopefully you've had a chance to practice. Let's go ahead and look at this. To me, this looks like we're going up by 1 every time. So I think my general term is going to have a slope of 1, and I'm going to use n just because I like n. 1n, and then we're going to test it. If I assume this is the first term, if you substitute 1 in here, you do get 1. If you substitute 2 in here, you get 2. I think that is my general term. So then my summation, okay, I'm going to start with an n of 1. My general term is 1n. And we say, well, we plug in 1, that gets my first term. We need to go all the way up. How far, though? Well, we want to finish with 40. And I think we could probably see if you replace n with 40, you do actually get 40. And here's my summation notation. Okay. Ooh, fractions. Originally, we thought fractions were scary. Now we realize that fractions are our friends, not food. We are going to look at this fraction line, and we're going to take a peek at the top. The top looks like we increase by 1 every time, so 1n. And then when we substitute 1 in for n, we do get 1. So I think this numerator is just 1n. Denominator, a little bit trickier. We are still adding 1, so this is also going to be 1n. But if we substitute 1 in here, you don't get 2. The only way you get 2 is if you add 1 on. And so I think there is my general term. Summation notation. I can work on my sigmas. They're usually pretty sloppy. I always like to start at 1. You can start at 0, whatever sounds good to you. General term, 1n divided by 1n plus 1. And then how far do we have to sum? Well, I bet you can see that we just have to go up to 14. Let's continue on. Oh, we've seen this before, right? This is the general format for a geometric sequence. It looks like we're multiplying by r every time, something like that, yeah? And it might even help if you looked at the individual terms of the sequence and saw that it was a times r to the 0th, a times r to the first, a times r squared, and so on and so forth. That might give rise to a general term of a times r to the nth, but then you have two options here. Because if this is your first term, substituting 1 in here gets you ar, which is the second term. So I think one option is you could put a minus 1, and then when you substitute in 1, you get 0, everything looks nicely. Or you can actually keep it this way, and when you do your summation notation, we're just going to start somewhere a little bit different. I'm going to do it this way just for a change of pace. We would need to replace the n with 0 first in order to hit this first term. But then how many terms, how far do I go? Well, if I plug in 10, I think that looks okay, right? Yeah, nothing bad there. And you'll notice it's actually 11 terms, right? 1 through 10 is 10 terms, plus the one before is 11 terms. More fractions, but again, we're pretty good at this by now. Maybe treat this as 4 over 1. Denominator, we're just adding 1 every time, so I think my denominator for my general term is just 1n. The numerator, again, looks geometric to me. We're multiplying by 4 every time. You could put like, yeah, no, I think we could probably just say it's 4 to the n and then see if we're right. Well, if we substitute in 1, we get the first term. Yeah, I think that's totally fine. So our summation here, we start at somewhere, we end at somewhere, 4 to the n over 1n. And I think we start at 1, because if you replace the n's with 1, you get our first term. And then we end with 9, because if you replace the n's with 9, we get our last term. Cool. Just a few more to go. Here it looks like we are adding 2 every time. Means my general term is going to have a slope of 2. But then if we replace n with 1, 2 times 1 is 2, not 1. I think we need to subtract 1 from here. Sigma notation-wise, we're going from somewhere to somewhere, and it's the formula 2n minus 1. Well, this one's a little trickier. We can start at 1, but how many terms out is this? Well, one nice little trick that you could do, and notice if I took, let's say this, I think you'd agree that 5 is the third term in here. What happens if I set 5 equal to my general term? You add 1 to both sides, divide by 2, you get 3. Oh, look, it tells you the input or the term number that generates that term value. So if I want to see where I'm going to end, why don't I just take that 21 and set it equal to 5n minus 1. 22 equals 5n. Uh-oh. Did something weird happen? Oh, it's not 5n. Like, we're getting a decimal. We shouldn't get a decimal for our input. It's the natural numbers. I think I'm getting 11 here. So I think we need to go from 1 all the way up to 11. Moving on through. Similar idea, but this one's going to be a little trickier. You'll notice that this one goes up by 4, and then by 6, and then by 8. So it looks to me like they have a common second difference. Quadratics are often useful to rewrite so we can see that pattern. I think 2 is 1 times 2, 6 is 2 times 3, 3 times 4, 4 times 5, and, you know, of course, so on. I think that gives us enough to see that the general term is going to be n times n plus 1, right? N and n plus 1. So when we have our sigma notation here, we're going from 1 up to somewhere of n times n plus 1. But then the issue is, how far to get to 90? Ugh. Well, it actually might help just to rewrite 90 as two consecutive numbers. Isn't 90 9 times 10? And notice you have your first term, second term, third, fourth. I think this is going to be the 9th term. If you weren't sure of that, you could have also taken the 90 and set it equal to the general term, right? So we get 90 equals n squared plus n. Subtract your 90, n squared plus n minus 90 factor, n plus 10 times n minus 9, and solve, and we end up with negative 10, which doesn't make sense with regards to terms, or positive 9. Moving on through, 4 to go. Let's see, what's happening here? 1, then a negative 2, then a positive 3. Oh, it's alternating in sign. Well, whenever something's alternating in sign, just treat everything as positives first. I think it might make your life a little bit easier here. Everything positive, let's go ahead and write that general term with a little space. We can see that we're going up by 1 every time, so we know it's 1n. When you substitute n to get 1, we get the right answer. Well, how do we make this alternate in sign? We just use that alternating factor. So let's put a negative 1 to the n, and then check. If we replace n with 1, we'll get a negative, but that's positive. Well, that's easy to offset, though. How about just n plus 1? Now when n is 1, you get a positive, and when n is 1, you get positive 1, and I think we're set. Sigma notation, n equals 1 up to, well, I think pretty clearly there are 17 values here, of negative 1 to the n plus 1 times 1n, or just times n if you would like. Fractions, but the top is just 1 every time, isn't it? And the denominator, I'm pretty sure we're multiplying by 3, right? Times 3 times 3, and we do that all the way out here for a while. Okay, so we know for our general term, we're going to have negative 1 to the n. I think when n is 1, that gives us the first negative. And then we're going to have a fraction, 1 on top, it's constant, divided by maybe 3 to the n. When n is 1, we get the negative. When n is 1, we get the 3, and I think we're doing just fine, right? You could even write it as negative 1 to the n divided by 3 to the n if you wanted to save some space. Okay? Or if you wanted to go even further, you could rewrite this as negative 1/3 to the n. All of those are equal. And I think from here we can get our sigma notation starting at 1 and going up, not to infinity, that's silly. Negative 1/3 to the n. How far do we go? Well, you can keep multiplying by 3 over and over again. You could do 3 to the n equals 729. I'm just going to multiply by 3. Another 3, so this will bring me to the fourth term, is 81. Another 3 is going to be 243. And I think yet another 3 is going to bring us to 729. So first, second, third, fourth, fifth, we're going up to 6 terms. 2 to go. Uh-oh. These ones are throwing curveballs at us. Now our patterns aren't just values, aren't just numbers. They actually have variables in them too. What is happening? Well, continuing this pattern, I bet this is 1 factorial. We could write this as 0 factorial. So we'll do the same thing we've done in the past. We'll separate the fraction or the pattern using the fraction line. Below in the denominator, it seems to be pretty apparently n factorial. And I think I'm going to be lazy here and just start at 0 so that when I do my summation over here, we'll start at 0. So that way I can just be lazy with my factorial. You could start at 1 and do n minus 1. Same idea. In the numerator, what's happening? Well, I think in the numerator, we're multiplying by x every time. So I think this is geometric. I think it's going to be something like 1 times x to the n. And if we start at 0, when n is 0, then that cancels it out, leaves us with 1. Yeah, and when n is 1, yeah, I think that looks pretty darn good. So we can just say x to the n, or 1x to the n. Where do we end? Well, we have to be careful here. Oh no, I guess this one's pretty easy because we end at 8 over here, and we just substitute an 8. Cool. 1 to go. One more of these. You'll notice that the 2 doesn't really fit the pattern, so I'm actually going to rewrite this so it does fit the pattern. And what is the pattern here? Well, it looks like you multiply the coefficients by 2 every time. Oh, by negative 2 every time. And you're also multiplying by an x plus 1 every time. So I think we could rewrite the 2 as 2 times x minus 1 to the 0th, and then move on from there so we can kind of see that general pattern. And so when I build this, I need to look at 3 different patterns. I need to look at the pattern of the coefficients. I need to look at the fact that they're alternating in sign. And I need to look at the fact that we multiply by x minus 1, and I'll try to color coordinate. So my general term here, I'll tackle the alternating sign first. I'll do negative 1 to the n. It looks like they start with 0, so I think I'll probably just keep this, because when n is 0, we're positive. If this is my first term, that's negative. That's what I want. That looks pretty good. The next thing that's happening is we're multiplying by 2 every time. Right? Now, if you rewrote these 2's, this would be 2 to the first, this would be 2 to the second, 2 to the third, and so on and so forth. So I'm going to call this 2 to the n. However, we already said this is going to be the 0th. And so if I plug 0 in here, 2 to the 0th isn't 2. I think we actually need to bump this 1 forward. I think this might have to be n plus 1. So when we replace this with 0, it looks pretty good. And then last but not least, x minus 1 to, I think, the n. Because if you replace n with 0, you get the first term, n with 1, you get the next term, so on and so forth. And I think we could probably go ahead and write this in summation notation as well, right? Going from 0 up to, well, we'll talk about that in a second. Then we have our formula, negative 1 to the n times 2 to the n plus 1 times x minus 1 to the nth. Check if you substitute 0 in for all the n's. Do we get what's up there? And I think we do, just doing a quick check myself. Yeah, it looks pretty good. Where do we stop? Well, they gave us this dot, 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 these ellipses here, and I think that means it goes forever. And we know how to write something that goes forever. How about just an infinity sign? And we should be good. So thank you for taking some practice on converting these summations of sequences to sigma notation. Lots of S's there. We are going to understand why we're doing this much more next class. Keep up the great work.